Hello, today we go look at some beautiful graphics made with Mathematica on the Raspberry Pi. You see the screen of a Raspberry Pi 5 here, and we're going to check if we have Mathematica on board. Yes, we have it. If you don't have it, look at Preferences, and then you see here Recommended Software. Click on it. It is updating the packages and finding the packages. And now all you have to do is look in Programming, and you see Mathematica. If you just click this box, click Apply, it will install. It's a big program, takes a while, it's about a gigabyte, but it will be worth it. And the notebook that we will study is on the web, so we go download this with a web browser. In my case, the default starts on wolfram.com Raspberry Pi. Wolfram language and Mathematica is free on every Raspberry Pi. Okay, let's download the notebook. We go to romani.ai, that's my website, /nb for notebooks, /manim with a capital -01.nb. Return, and yes, to the upper right we see it is downloaded. We can close the browser and we go to the file manager, to the downloads directory, and here we see manim. We double click, and now Mathematica is starting. You see we have a welcome screen. We can close this, and we have here our notebook. Let's also close the file browser and put the notebook right in front. If you want the notebook a little bit bigger or smaller, just press Ctrl and roll the mouse wheel, and you see that you can nicely make this. In the lower right, you see that you can also change all kinds of magnification factors. My name is Bart Romani from Eindhoven University of Technology, and we're going to have a next example of 21st century computing, how to make beautiful interactive graphics. And as an example, I take the beautiful interactive graphics from the beautiful graphics from 3Blue1Brown. That's Gary Grant from Khan Academy. They're quite impressive, and we're going to look at his example on constraint optimization. Let's have a look at YouTube, where he's explaining this.
Here is the graph of f of xy equals x squared times y. And now this constraint, x squared plus y squared, is basically just a subset of the xy plane. So if we look at it head on here, and we look at the xy plane, this circle represents all of the points xy such that this holds. And what I've actually drawn here isn't the circle on the xy plane, but I've projected it up onto the graph. So this is showing you basically the values where this constraint holds, and also what they look like when graphed.
It's beautiful and wonderful, and let's make this specific graph interactively, and you will see that it is very easy to make it. Normally, he uses the proprietary package manim that he wrote for his visualizations. But if you try to download manim, install it, and then try to figure out the code, it's not easy. It's actually quite difficult to read for a non-expert. And I'll go show you how you can do this in Mathematica. And you see, by the way, all these formulas are still written by hand, and in Mathematica there's no need for that anymore. You can easily write everything in mathematical notation. So what we're going to do is I take you through this computational essay. You see we have here cells, and all these cells, they are text cells, and we're going to intermingle them with code cells. So we're going to do some writing. You saw the earlier YouTube movies of me, otherwise check it out, youtube.com/21st century coding. Round brackets are for grouping, curly brackets are for lists, and square brackets are for functions. And if you want to have some symbols, Control head is for superscript, and escape before and after a letter, escape P, escape, you get the pi. Let's do it. I type escape P, escape, and you get the pi. Okay, we do not keep numbered outputs, so this is a specific way. Then this system variable, we put history length, we put that to 0. And I pressed Shift, Return. Now you see the first cell has been executed. This is in number 1. You see that this type of font is an input cell. You can see it here. This type is input, and if I click it here, I have a text cell. So here you can see what type of cell do I have. Okay, we have the first function here, x square y. If you want to type it, for example, let me type it again. You say x and then control head, and then you get a square, and then y. Yeah? It's yellow because this is math notation. But just as in LaTeX, you have mathematical notation. So what we're going to do is we have the function here and we want to have the contour. X square y is z, and this is a double is because it is not an assignment, it's not is for, but it is equal to. And we plot it for x from -2 to 2, y from -2 to 2, and z the same. So let's make a contour plot. Okay, quite nice. It looks already that's exactly what we like to have, and you see even on the Raspberry Pi it's quite fast. But it's not exactly what we like to have. We have a mesh. So I indicate in yellow here, and if you want to make this yellow, just highlight your text, look at format, and you say the background color, and I don't make it none because it is already yellow, but you can make it any color you like. So we take only the function x squared plus z, x squared y is z, and now we do mesh is false. Okay, but the color is not right yet. We need it blue. So what we will do is we use the color picker from the insert menu, and we see now that we add another option. Contour style will be RGB color 0.51,1. Let's do. Shift return, and now nicely we get a blue surface. How do we get this color? Well, it's called RGB color, and this is R, G, and B. And if you want to insert a color, let's insert here a new color, you can just say insert color, and then a palette comes open. For example, I want bluish. Then you can select here a little bit from lighter to dark. So let's say I take this particular blue, and then you say OK. Okay, I'm pretty close, 0.5, and it's almost 1. But you can pick any color here and just insert it as you like. We have it blue, but we still have some artifacts here. And we need specularity. Well, specularity we can just add after contour style, comma, and then we add specularity. And we do that by adding a white light source with specularity 100. Let's do it. And now we see indeed we have a very nice specularity. And you see the, the motion on the surface. What is specularity? If you highlight with your mouse and you say, okay, get help, then a window opens and you go to the Wolfram documentation. And here you see this Wolfram documentation with 30.3. We have now put version 14, but for graphics it's all still the same. So specularity, you say you have specularity S or S, N. And what we can do is we take an example, and here we say, for example, we have specularity white, N, and N can be 5, 20, or 100. And if we take 100, we get specularity like this. And that's what we want. There are many other examples, different light sources, and so on. Please check it out. So now we have specularity white, 100. But we also need the lighting. And the lighting, let's first do it. We add by adding lighting to accent. And we go in the documentation how that works. And now you see we have proper lighting. We have only a single light source. There is no other shade or whatever we like to have. We have just specularity on the blue surface. And this lighting, how does it work? We go get help again. The window opens. And now we see the full documentation of lighting. And if you look in the details, you say, okay, you can have all kinds of settings. But if you say it's a specific name, well, standard gives you 3 light sources in different color, neutral, white light sources, but we want a single one, and that's called accent, and this is exactly what we want. We don't want 3 points, but we want accents, and that's exactly what we did. So always look at the documentation, and you find many, many examples on how to do that, from you name it. So now we have a nice surface, and everything is, of course, immediately rotatable. You can click on it, and you can make it smaller and larger. If you cut, copy, paste, save graphic, you name it. If you say I want a default view, then it immediately jumps to the default view. Now we're going to add the cylinder. So now you see we do a contour plot 3D of this function, comma, that function, and now we have a list of functions, so it's in curly brackets. All the rest is the same. And now let's see if we have two functions. Okay, we have two functions. This is the surface in blue that we had before, and this is a cylinder. You see that is the equation of a circle, xy plus y square, and this is for all the values of z, where the circle has the radius of 1, and it's a cylinder, and you can look inside, and that's exactly what it is. And of course, what we are after is where these two curves intersect. And the cylinder we can make yellow. Well, how do we do that? Just we say that we want the circle to be yellow and that the opacity should be 0.4. Well, opacity, that means, and it's all embedded in contour style, by the way. So if I see a contour style here and I press Control point, you see Control point always finds the matching brackets and what's in there. So it's at this specific color, make the surface, then make a specularity white, comma 100, comma, and then go to, this is for the first surface, so you see the first list, and this is for the second surface. So the second surface is yellow, opacity 0.1. Okay, let's have a look. Wow, it works. So now we have a yellow cylinder, and you see how beautiful it is. We can make opacity, and that's 1 minus transparency, and now we can look through, and we have a transparent cylinder here. Boundary style is what we want next. So we're going to do the boundary style, because we really want the boundary. And then we say, okay, the boundary style of surface number 1, there is no boundary here. If you want a yellow boundary here or a purple boundary, you get it right here. The cylinder, we also want no boundary. But the boundary between 1 and 2, we want red. And this is how easy you can indicate the boundary. Mathematica underwater completely finds out where these boundary points are. And let's see what it does. And indeed, we get them as a red line. We see the boundary here. Suppose we want the boundary here, for example, purple. It's difficult to see, but let's make it also red. That's easier to see. Now you see we have a red line as well on boundary number 1. I just indicate how easy it is. We make it none again. But it's a little bit thin. We want to have it thick. And we want also the number of plot points. You see it's a little bit few plot points, so we take a little bit more. So we add plot points that we make 20 of them. And the style is not red, but we make now a couple of graphics primitives. We make it red and thick. So let's see what happens now. And now you see we have beautiful graphics, indeed what we want. A transparent cylinder. If we remove the cylinder, we have exactly the figure that we need. The red contour is now much bigger. It is thicker. And now we want to make the arrows. The arrows is very simple. It's a graphics 3D. And we give it first the primitive. So we say, okay, we make it arrowheads. How big are they? 5% of the graphics width. And then we make an arrow. And we make an arrow of a tube that starts at the origin, 0, 0, 0. And it runs to x is 0, y is 0, and z is 1.5. This is the second arrow. And we make 3 arrows. And let's just do it. This is now my set of arrows. You see nicely a tube, they have a beautiful 3D arrowhead, and they are in 3D. And I call this whole 3D figure, I call it arrows. So this is a 3D graph that's called arrows. And I can show them both. So I say, okay, open my function with a square bracket, and then there comes a list. The first one is this contour plot. And if I just see contour plot and I press control point, you see this is my contour plot. And this is what I added. I highlighted this in yellow. So after the contour plot, I get a comma, and then I get the second element, that's the graphics 3D. It enters here, and this is the last bracket that closes show. So now I show them both. The contour plot 3D with the two surfaces, with the red intersection, and now you have all the and the arrows. Make it as nice as possible. So we want to remove the box, and we want to make the background black. So we add no axis is false, boxes are false, and the background is black. And we want the opacity 0. That means we don't want to see the cylinder anymore. And now we have exactly the figure that 3Blue1Brown was showing. And you see, even on the Raspberry Pi, Mathematica is extremely fast. You can beautifully rotate this figure. You can even do more. And what we can also do is that we have a very nice colored contour style. We can add a texture. And in this case, I just took a picture of clouds. I took it from a website and just copy and then paste it right here. You can have pictures in your code. And now you see, okay, I want to have a texture on the surface of number 1. And then I also want the boundary style, not red, but I want to have it a little bit more complicated. I want to have it pink, I want to have it thick, and I want to have it dashed. And the rest is the same. So let's have a look. And now it is making my figure. And now you see I have beautiful clouds on my surface. I have a dashed pink contour between the two. And this means with just a few strokes, you can just add anything. It's just with a few commands and it's fully interactive. You can make it as you like. If you want another picture, you just say, okay, I remove this picture. You open a browser and you say, okay, I want to have forest. And here I'll show some images. And now let's say, okay, take a forest. What shall I take? I take this forest. And now I say, copy image. And then go back to my Mathematica notebook. I go to this place here and I say paste. And now I have my forest. And now if I run it again, you see how easy you can get. And now I have a forest on my surface. So no matter it is in a few lines, you make whatever you like. We can even go a step further, and these line segments we want to blow up, and you saw that we had these arrows, they were tube segments. So let's make the line segments that are drawn in this figure into tube segments. Well, we need to replace them, and there's a command, replace all. So let's have a look at this command. Here we go to the browser and we see replace all. You can make a short version by /point. And if you replace, for example, you have x squared, y, z, you replace x by 1. You see you get 1, 1, y, z. Replacement is, as it says, you replace. So if I have my complete original code, and I just say replace /point, all the line commands, and the lines means this is an underscore here, and that means anything. So an underscore is any pattern, and we call it X. And then replace that by tube. And of course, that should be the same X, so the same pattern. And this is the thickness of the tube, 0.3, so 3%. So now every line in this boundary style underwater. It's a very complex representation, but I don't care. I just say replace all these line elements by tube elements, and now let's see what happens. And now you see it is very nicely made into a tube. If I make the tube bigger, I just have to say, okay, make this 6 and render it again. And now you see I have a really thick tube. So it's extremely easy to manipulate whatever you like. Oh, manipulate. Let's manipulate the radius of the tube. That's nice. So I have the same code again, and now I make the tube radius variable. So I just put manipulate in front. So I say manipulate square bracket that opens the function. Here I have my complicated show, including the graphics. It ends here. And then I say manipulate this whole thing, comma, for the tube radius. And the tube radius should go from 0.01 to 0.1. And I also manipulate the opacity between 0 and 1. So we got two sliders, one for the tube radius and one for the opacity. Let's have a look. And now you see, okay, I have the tube radius here. And if I make the tube radius another style, you see, I can just click on the slider and my tube radius gets the value that I really like. If you open this with a plus, you see exactly, okay, this is now 0.8 tube radius. And the opacity I can change by just clicking on the slider. And of course it's fully 3D, so if you move this, it's fully interactive and it's beautiful. You can really change any parameter on the fly. Okay, it works beautifully. You can rotate it, zoom it. If you press the control key, you can zoom in. You can, well, whatever. This is zooming in on the window. You can pan, and this is an explanation of how it works. The replace all. I showed it before. If you replace the B into 4 is this. But in functions, we saw it before that we changed the lines into tubes. We had a function, and this means the underscore is anything. And this says the function is x squared. So if I run this function, and I take down the function of 3, of course you get the square of it. So this is the way how you say a function of something is something new. This means a delayed assignment, so it's not directly is. And here, by the way, you see if I take the function of monkey, you get monkey squared. Well, what means delayed assignment? If I take fx, for example, is the date, I get the current date of today with the time, etc. And if I do the delayed assignment, I call it f2. Now you see the difference. If I ask for x1, for f1, you get the original date. But if I ask for f2, it's only evaluated when you call it. And now you see I get a new time. So this means rule delayed. And the same way as s delayed. So if you take escape semicolon larger than escape, you get it. Let's do it. Escape semicolon larger than escape, and now you get it. In the last section, we're going to generate a movie, and we generate the frames for a slowly rotating graph. Okay, the frames, we generate them as a table. So we make a movie, and we say that's a table of our full code that we discussed before. We start at a specific viewpoint, and then we say, okay, this table runs the code, that's the visualization code, and this is phi, runs from this beginning, minus pi over 2 minus something, to minus pi over 2 plus something. In very small steps, 0.0.5. But there's an interesting thing. We're going to use parallelize. And parallelize means that Mathematica automatically uses all the 4 cores of the Raspberry Pi 5. Let's show it. We make this window a little bit smaller, and we look at the system tools, and we start a system monitor so we can nicely see. On top you see the 4 graphs of the 4 CPUs of my Raspberry Pi. Okay, make this a little bit smaller so we can see at the output what happens. I start parallelize. You see that automatically parallel table is started, and all the 4 cores are now heavily working, and they do so until all these frames are being generated. So you see we have 12 sets of 4 items each, so 4 kernels are working in parallel. This takes some time. In total it will be 2 minutes, I think. Okay, it's done. We see that the kernels now come to rest. Really nice, we have this parallel opportunity. Okay, we close this again and we make this bigger. And now what we're going to do is we expand the movie with the frames in reverse. So we say join the movie with the reverse of the movie. And again, of course, join is with a capital, reverse is with a capital. We have the square brackets for the function, and everything is plain English. Join the movie with its reverse of the movie. And we're going to export it to where? The notebook directory, and this is string concatenate with movie.ai, movie.avi. Okay, let's do it. And now it's processing the expression for video export. Okay, it's now home Pi downloads movie. You see how easy and powerful everything is in Mathematica? Well, of course, we need to see the movie, of course. So let's go to the file manager and go to the downloads directory. And there's our movie. Double click. And yes, it runs and it goes back. Okay. Thank you very much.